All right, let's deep dive into databases,
Okay.
specifically relational database management systems.
RDBMS.
Yeah, RDBMS, the systems that power, well, pretty much everything digital.
Mm.
You sent over some lessons on this topic, and I have to admit, when I
Hmm.
first glanced at it, it looked a little dense,
It is.
even for me.
Yeah, it can be a lot to take in.
Yep, but that's what we're here for, right?
Exactly.
Break it down, make it make sense, and by the end of this, you'll be able to hold your own in a conversation about RDBMS.
Hmm.
You'll understand how these data relationships work,
Yeah.
and maybe you'll even start thinking about how to make databases really efficient.
Mm.
Think Facebook, Amazon, your bank, they're all using these principles.
Every time you go online, you search for something, you buy a product, you post a comment, it's all powered by a relational database.
So to kick things off,
Okay.
let's talk about database management systems in general.
So a database management system, or DBMS, is basically a system for creating, organizing, and accessing data.
Okay.
Think of it like a really organized digital filing cabinet
Okay.
that multiple users can access.
Yeah.
And a DBMS handles three main things: the data itself, the engine that allows you to work with that data,
Okay.
and the schema, which is like the blueprint that defines how the data is structured.
Okay, so I think I'm following so far.
Good.
So where does RDBMS fit into all of this?
So RDBMS is a specific type of DBMS that organizes data into tables, with rows and columns,
Okay.
kind of like a spreadsheet, but on steroids.
Mm.
It's designed to handle much larger and complex data sets.
Okay.
And the beauty of this model is its simplicity and efficiency, which is why it's so widely used.
Makes sense.
Systems like SQL Server, Oracle, MySQL, even Microsoft Access are all examples of RDBMS.
So we've got these tables, but what's actually in them?
Yeah.
Like what's the official lingo
Right.
for the rows and columns?
So each row in a table represents a single record.
Okay.
Firstly, it's called a tuple.
Tuple. Okay.
And columns, they're called attributes, and they hold specific pieces of information about that record.
Okay, so like a row or a tuple
Uh-huh.
could be information about a specific customer.
Yes.
And the columns or attributes would be things like their name, address, order, history.
You got it.
Okay.
And to keep things organized and prevent chaos, we use primary keys.
Primary keys. Those sound important.
They are.
Okay.
A primary key is a unique identifier for each row in the table.
Okay.
Like, think of it like a social security number for data. It guarantees that each record can be identified
Right.
and retrieved quickly.
Makes sense.
Now, we can also have composite keys, which combine multiple columns
Okay.
to create a unique identifier
Got it.
if a single column isn't enough.
Okay.
And then there's the overall structure of the table,
Uh-huh.
which we call the relation schema.
Okay, so the relation schema is like the blueprint.
Yes.
This defines all the attributes and how they relate to each other. Got it. Now, how do we actually talk to these databases?
Right.
And get them to do what we want?
That's where SQL comes in, structured query language.
Okay.
It's the language that lets us interact with the database.
So it's kind of like having a conversation with the database, asking it questions, giving it instructions.
You could say the SQL lets you do everything from retrieving specific information to adding new data, updating existing records, deleting information, even defining security permissions.
Wow. That's a lot.
It's pretty powerful.
It is powerful, but with all this data flying around, how do we make sure it's accurate, reliable, especially when we're dealing with sensitive information?
Right, that's where ACD properties come in.
ACD properties, okay.
Atomicity, consistency, isolation, and durability.
Okay.
They're like the unsung heroes working behind the scenes
Yeah.
to guarantee data reliability.
Okay.
So think about it. Let's say you're making an online purchase.
Right.
You wouldn't want the transaction to be half finished,
Yeah.
or for the system to lose track of your payment, right?
Yeah, absolutely not.
The ACD properties are there to make sure everything happens smoothly and reliably.
Okay. I'm intrigued. Let's break it down.
Okay.
What does atomicity mean?
Okay, atomicity means that a transaction, which can be a series of operations, is treated as a single unit of work.
Okay.
It's all or nothing. Either all parts of the transaction complete successfully,
Right.
or the entire transaction is rolled back as if it never happened.
Okay.
This prevents data from ending up in a partially completed or inconsistent state.
Got it. So no half-baked data floating around.
Exactly.
Okay, what about consistency then?
So consistency ensures that the database always remains in a valid state,
Yeah.
meaning that any changes to the data must follow predefined rules. For example,
Yeah.
if you delete a customer record, you wouldn't want their orders to still exist
Right.
without a corresponding customer.
Right.
Consistency makes sure that operations are completed in a way that maintains data integrity.
Right. So it's like the guardian of the database rules,
Mhm.
making sure everything stays in order.
Exactly.
Now, what about isolation? Does that mean each transaction kind of happens in its own little bubble?
In a way, yes.
Okay.
Isolation ensures that multiple transactions happening at the same time don't interfere with each other.
Okay.
It's like having separate lanes on a highway.
Right.
Each car stays in its lane to avoid collisions.
Gotcha.
This prevents conflicts and ensures that each transaction sees a consistent view of the data.
It's like having multiple chefs in the kitchen.
Yes.
And they're not bumping into each other or mixing up ingredients.
Exactly.
Okay, last but not least,
That's durability.
durability guarantees that once a transaction is complete
Okay.
and committed to the database, the changes are permanent,
Okay.
even if the system crashes.
Even if the system crashes.
Think of it like writing something in indelible ink.
It's there to stay no matter what.
Okay.
These changes are recorded in a way that allows them to be recovered even after unexpected events.
So even if a server, melts down,
Yes. The data is safe.
the data is safe.
Okay, good.
These ACF properties are really crucial
Yeah.
for maintaining data integrity, consistency, reliability. They're the foundation of trust in any database system.
Okay, so we've got our data organized into tables. We've got SQL to communicate with it. We've got these OCD properties keeping everything running smoothly.
Right.
Now, how do we actually plan and design these databases? Because it seems like there are a lot of moving parts.
You're right, it can get complex.
Yeah.
And that's where data modeling comes in.
Okay.
It's like creating a blueprint before you build a house.
Okay.
It helps us visualize the data landscape,
Right.
define relationships between different pieces of data, and design the structure of the database.
So it's not just like throwing data into tables and hoping for the best.
Definitely not.
That'd be like building a house without any plans.
Yeah.
You just end up with a chaotic mess.
Right.
Data modeling helps us avoid redundancies and inconsistencies
Okay.
and ensures that we build a robust and efficient database that actually meets our specific needs.
Gotcha. So what tools or methods are used for data modeling?
One of the most common tools is the Entity Relationship Diagram,
Okay.
or ERD.
So it's like a visual map of the database.
Exactly.
Okay.
An ERD visually represents the entities, which are the things we want to store information about,
Okay.
and the relationships between them.
Okay.
Since in a library database,
Yeah.
entities might include books, borrowers, and authors,
Right.
while the relationships could be like borrows or writes.
So ERDs help us understand what data we're dealing with and
Yes.
how it all connects.
Exactly. They're essential for planning and designing an effective database.
Okay.
And they help us avoid redundancies and inconsistencies and a whole lot of headaches down the line.
All right. So we've got our trusty ERDs to guide us,
Yes.
but there are different types of relationships between entities, right?
You're right.
Didn't you mention one-to-one, one-to-many, and many-to-many?
Absolutely.
Okay.
There are 3 fundamental types of relationships in RDBMS,
Okay.
and each one plays a crucial role in how we structure and connect our data.
Okay, so let's dive into those relationship types.
All right.
First up, one-to-one.
Okay.
What does that look like in the real world?
So a classic example of a one-to-one relationship is a driver's license.
Okay.
Each person has one driver's license,
Right.
and each driver's license belongs to only one person.
Right. So it's unique.
It's a unique pairing.
Gotcha. So each entity on one side of the relationship is connected to exactly one entity on the other side.
Exactly.
Okay. What about one-to-many?
Think about a customer and their orders on an e-commerce site.
Okay.
One customer can place many orders,
Right.
but each order belongs to only one specific customer. That's a one-to-many relationship.
Okay.
One entity on one side can be related to multiple entities on the other side.
Right. It's like a parent with multiple children.
Exactly.
Each child only has one parent.
Exactly.
Okay, that makes sense.
All right.
Now for the potentially more complex one.
Yes.
Many-to-many.
Many-to-many relationships are all about capturing connections that go both ways.
Okay.
So, for example, students in classes.
Okay.
Each student can enroll in many classes,
Right.
and each class can have many students.
Got it. So it's like a social network.
Yes.
One person can have many friends, and each friend also has their own network of connections.
Exactly.
Okay.
It gets a bit more complex to model this type of relationship in a database,
Okay.
but we have techniques for that.
We'll have to dive into those techniques later.
Yes.
But I think we've got a good grasp of the basic relationship types.
Good.
So we've mapped out our data, defined relationships, and we're almost ready to build our database. But wait, isn't there one more crucial piece of the puzzle?
Yes.
Something about normalization.
You have a great memory.
Like,
Normalization is a critical step in the database design process.
okay.
It's like tidying up and organizing your data
Okay.
to make it more efficient, consistent, and reliable.
I'm all for tidying up and avoiding messy data.
Good.
But what exactly does normalization involve? It sounds a bit intimidating.
It might sound complex, but the core idea is pretty simple.
Okay.
Normalization is all about reducing data redundancy.
Okay.
Imagine having the same information scattered throughout your database,
Okay.
like customer addresses repeated for every order they place.
Oh, yeah, I see.
It's inefficient.
Yeah.
It wastes space.
Right.
It makes updates a nightmare.
Mm.
Normalization helps us avoid all that
Okay.
by breaking down data into smaller, more focused tables
Okay.
and establishing clear relationships between them.
So it's like taking a big messy pile of clothes
Yes.
and organizing them neatly into drawers and closets.
Okay.
I like that.
Normalization helps us create a well-structured database
Okay.
where each piece of information has its designated place,
Mm-hmm.
making it much easier to manage, update, and analyze.
Gotcha. And we do this using what's called normal forms.
Yes, normal forms.
Okay, it sounds like we're entering a data dojo or something.
It's not that intense,
Okay.
but you think of them as levels of organization
Okay.
or steps in the tidying up process.
Right.
The most common ones are first normal form,
Okay.
1NF, then second normal form, 2NF,
Yeah.
and third normal form, 3NF.
Okay, so 1NF is like basic level.
Yes, 1NF is about making sure every attribute in a table is atomic,
Atomic. Okay.
meaning it can't be broken down further.
Okay.
Then 2NF eliminates redundancies that depend on only part of a composite key.
Right.
And 3NF removes transitive dependencies, where an attribute depends on another attribute that's not part of the primary key.
Okay, so it's like a multi-step process of refining, organizing data, making it as efficient as possible. I think my brain needs a break
I agree.
to process all this normalization.
We've covered a lot of ground today.
Yeah.
From DBMS and RDBMS,
Mm-hmm.
SQL ACD properties, data modeling, normalization.
It's been a journey,
It had.
but I feel like I'm starting to get it.
Good.
These powerful systems that we take for granted.
Yeah, they're everywhere.
They are everywhere.
What's
So
for part 2?
join us for part 2 of this RDBMS deep dive.
Yes.
Where we'll explore some real-world examples of these concepts in action.
Okay.
See you there.
See you there.
So last time we left off talking about normalization,
Yeah.
Organizing that data,
Right.
reduce redundancy,
Yeah.
ensure data integrity.
Yeah.
But how does that actually play out,
Mm.
like in a real world scenario?
So imagine you're building a database
Okay.
for a music streaming service like Spotify.
Okay. Yeah.
You'd have information on artists, albums, songs,
Right.
and of course, millions of users.
Mm.
Without normalization,
Yeah.
you might end up with like a lot of repeated information.
Okay.
So, for example, an artist's name
Yeah.
and genre
Right.
could be duplicated for every single song.
Okay. Yeah. I see how that could get messy.
Yeah, especially with millions of songs.
Right.
It would get really inefficient.
Yeah.
So normalization helps us break that down
Okay.
into smaller, more manageable tables.
Okay.
So you'd have a separate table for artists, another one for albums, one
Yeah.
for songs, and so on.
Okay.
And each table would contain
Mhm.
only the information that's directly relevant to that entity.
Right.
And then we'd use relationships,
Okay.
like those foreign keys we talked about,
Yeah.
to connect the tables.
So instead of repeating the artist's name and genre for every song,
Right.
you'd just have like a unique ID.
Yeah, a unique ID for the artist
In the song table.
in the song table, exactly.
That links back to the artist table.
Right.
Yeah.
So that way, if an artist like changes their stage name, you only have to update it in one place,
Makes sense.
the artist table.
Yeah.
And then that change automatically ripples through the entire database.
Because of those relationships?
Yeah, thanks to those relationships.
Okay.
So no more like hunting down and fixing all those duplicate entries.
Yeah, that would be a huge time saver.
It is.
And I bet it makes the database a lot more efficient, too.
Absolutely.
Oh,
Less
well.
storage space,
Yeah.
less storage space, better data consistency,
Yeah.
faster updates and queries.
So it's like a win-win.
It's a win-win all around.
Normalization, it's like the Marie Kondo of databases.
I like that.
Sparking joy by getting rid of all that clutter.
Exactly.
All right, so what about those relationship types we discussed? Can you give me some more concrete examples
Yeah,
of
sure.
how those actually work in practice?
Let's start with that one-to-one relationship.
Okay.
Think about a scenario
Okay.
where each employee in a company
Hmm.
is assigned a unique parking space.
Okay.
One employee,
Yeah.
one parking space.
Yeah. Right. It's a simple link.
It's a very direct link.
But in the database, wouldn't you just
Yeah.
include the parking space information
Mhm.
in the employee table?
Sometimes you could,
Okay.
but let's say the parking situation is more complex.
Okay.
Maybe some spaces are reserved for executives,
Uh-huh.
others are for visitors.
Right.
Some have, like, special access requirements.
Okay.
In that case, it might make sense
Yeah.
to have a separate parking space table
Right.
with all those details.
Gotcha.
And then you'd link the employee table
Uh-huh.
to the parking space table
Okay.
using a foreign key.
So even with a one-to-one relationship, sometimes
Right.
it makes more sense to have separate tables for
Exactly.
better organization.
Yeah, better organization, more flexibility.
Okay.
It really all depends on the specific needs of the database
Right.
and how complex the information is.
Okay. That makes sense.
All right, let's move on to one-to-many relationships.
Okay.
Classic example is an online store. With customers and orders,
Right.
one customer can place many orders,
Mm-hmm.
but each order is associated with only one customer.
Right.
So the customer table would have information like the customer's name,
Okay.
address, contact details,
Yeah.
while the order table would contain details about each specific order,
Great.
including a foreign key,
Okay.
linking it back to the customer who placed it.
Gotcha.
This structure lets you easily retrieve all orders
Uh-huh.
placed by a specific customer
Okay.
or analyze purchasing patterns
Right.
across different customer segments.
Which is useful for, like, marketing.
Very useful for marketing and sales.
Sales, yeah.
Mm-hmm.
Okay, now for the grand finale.
All right.
Many-to-many relationships.
Yes.
Those always feel a bit more mind-bending.
They can be a little trickier to model,
Yeah.
but they're incredibly powerful
Okay.
for representing complex connections.
Okay.
So think about a movie database.
Okay.
You'd have a table for movies
Uh-huh.
and a table for actors.
Right.
Now, one movie can have many actors,
Right.
and one actor can be in many movies.
It's a two-way street.
It is. You can't just assign one actor to one movie.
Right.
It's a web of connections.
Gotcha.
So to model this in a database,
Yeah.
we use a special kind of table called a junction table,
Junction table. Okay.
sometimes called a bridge table
Okay.
or a linking table.
Gotcha.
This table sits between the movie table
Right.
and the actor table,
Okay.
and it connects them.
So instead of trying to cram all that into
Yeah.
the movie or the actor table,
Right.
you have this separate table that's like a bridge.
It's like a bridge, exactly. So
Yeah.
the junction table would have two foreign keys,
Okay.
one pointing to the movie ID
Mm-hmm.
and one pointing to the actor ID.
Okay.
And each row in this table
Okay.
represents one specific actor-movie connection.
Got it.
This way, you can easily see which actors starred in which movies,
Right.
and vice versa.
It's a clever way to handle those relationships.
It is.
So I'm starting to see how these relationship types
Yeah,
are like the building blocks
they are.
of a well-structured database.
Exactly.
They let us model those real-world connections and
Ah.
complexities
Right.
in a way that makes sense.
Yes, in a way that makes sense and is efficient to manage.
Right.
It's all about finding the right structure to capture those connections and making that data work for you.
Okay, so we've covered normalization, different relationship types. We've seen how those concepts can be applied in the real world,
Yeah.
like music streaming services to movie databases.
Exactly.
I'm feeling a lot more confident about my database knowledge now.
That's great to hear.
But you mentioned some exciting trends and challenges.
Yeah, there's always more to explore in the world of databases.
Okay.
In the next part, we'll delve into some of those emerging trends and challenges,
Okay.
like NoSQL databases
Okay.
and the growing importance of cloud computing.
Sounds fascinating. I'm ready to keep diving deeper into this world of data.
Join us next time.
Join us next time as we explore the future of databases. All right, welcome back to the final part of our RDBMS deep dive.
It's been fun.
We've covered a lot
a lot of ground.
from fundamentals
Yeah, the
of
basement.
relational databases
Mm.
to normalization and those relationship types.
Yeah, all those relationships, so important.
And we've seen how those concepts
Yeah.
play out in the real world, like
Real-world examples.
online stores and movie databases.
Yeah, it's fascinating to see it in action.
It is, and I'm feeling a lot more enlightened, I guess, about the data structures
Yeah.
that power so much of our digital lives.
It really is the backbone of everything.
It is, but you mentioned some
Yeah.
exciting new trends and challenges,
Some new things on the horizon.
like NoSQL databases and the rise of cloud computing.
Right. Those are big ones.
So I'm curious to hear more about those.
Yeah, definitely. The data world is always changing.
Yeah.
And while RDBMS has been king for so long,
Mm-hmm.
for decades,
Right.
there are new players emerging,
Hmm.
to address the unique demands
Okay.
of modern applications.
So, what are we talking about here?
So one of the most prominent trends is the rise of NoSQL databases.
NoSQL. That sounds kind of rebellious,
Yeah.
a challenge to the established order.
It is like a shift in thinking.
Okay.
So NoSQL stands for not only SQL,
Hmm.
and it represents a departure from the traditional relational model.
Okay.
NoSQL databases are designed to handle massive data sets
Okay.
and those flexible demands of modern applications,
Gotcha.
particularly in areas like big data,
Yeah.
cloud computing, and real-time analytics.
So it's like RDBMS is the seasoned veteran.
Yeah, the old guard.
And NoSQL is like
The up-and-comer agile startup.
The agile startup, exactly.
Okay, so they both have their strengths and weaknesses.
To do.
Right,
Yeah.
tool for the job type of thing. Exactly. So RDBMS,
Mm-hmm.
it's still the gold standard for applications that require strict consistency,
Okay.
transactional integrity, like, think financial systems,
Yeah.
inventory management.
Matrix.
But NoSQL databases,
Yeah.
they offer advantages
Okay.
in terms of scalability,
Uh-huh.
flexibility, and performance,
Okay.
especially when you're dealing with unstructured or semi-structured data.
Okay, so besides the obvious,
Yeah.
the SQL versus not only SQL,
Right.
what are some of the key differences between RDBMS and NoSQL?
So one key difference is the way data is structured.
Okay.
RDBMS relies on a fixed schema,
Okay.
which means you define the structure of your tables and columns up front.
Okay. Yeah.
NoSQL databases, on the other hand,
Uh-huh.
often use a more flexible schema
Mm.
or even schemaless approach,
Okay.
allowing you to store data without predefining its structure.
So it's like the difference between
Yeah.
having a blueprint for a house
Yeah.
versus just kind of building it as you go.
Yeah, adding rooms and features as you go.
Okay. And this flexibility makes NoSQL better for...
It makes it great for handling rapidly changing data or
Mhm.
data with unpredictable structures like social media posts,
Right. Yeah.
sensor data, or user activity logs.
But doesn't that flexibility come at a cost?
It can, yeah.
What about data integrity and consistency?
That's a valid concern.
Yeah.
While some NoSQL databases do offer ACD-like guarantees,
Mm-hmm.
they often prioritize availability
Mhm.
and partition tolerance over strict consistency.
Okay.
This means that in some scenarios,
Yeah.
you might have slightly outdated or
Okay.
inconsistent data, especially in distributed systems.
So it's a trade-off.
It is, yeah.
You gain flexibility,
You get the flexibility,
but maybe you lose a bit of consistency.
a bit of consistency, yeah.
Okay, it depends what you need.
Exactly. It all depends on the application.
Right.
For something like, social media feeds.
Yeah.
A little bit of inconsistency might not be a big deal,
Right.
but for financial transactions,
Yeah.
you definitely want that rock-solid ACD guarantee.
Right. Makes sense.
So NoSQL is definitely shaking things up in the database world.
Yeah. You also mentioned cloud computing
Right.
as a major trend.
Big trend.
So how is that impacting data management?
Well, the cloud is having a huge impact
Okay.
on how we store, manage, and analyze data.
Mm-hmm.
So traditional data warehouses,
Yeah.
often expensive and complex
Right.
to set up and maintain,
Yeah.
required specialized hardware and software.
Yeah, I can imagine.
It was like building your own power plant.
Right.
But with cloud platforms like AWS,
Yeah.
Azure, Google Cloud,
Mm-hmm.
we can leverage their infrastructure
Yeah.
and expertise
Mm-hmm.
to create scalable and cost-effective data warehouses.
So more like renting the power plant.
Exactly, renting the power plant.
Okay.
And this allows organizations of all sizes
Right.
to access really powerful data analytics capabilities
Okay.
without that huge upfront investment
Right.
and those maintenance headaches.
So cloud data warehouses, they offer flexibility.
Flexibility, scalability, to scale up, scale down,
Okay.
as needed,
Mm-hmm.
paying only for what you use.
It's like data center on demand.
Data center on demand, exactly.
Okay.
Plus, with the cloud, you get access to all these tools.
Oh, yeah.
Data management, analytics
Oh,
tools,
what kind of tools?
machine learning algorithms,
Okay.
data visualization, dashboard.
So it's like a whole ecosystem.
It is,
A
yes.
whole ecosystem at your fingertips.
So from NoSQL to the cloud,
Yeah,
sounds like the data landscape is undergoing a major transformation.
it is a major transformation.
And these trends are kind of intertwined.
They are very much intertwined.
Right.
Many NoSQL databases are actually designed specifically for the cloud,
Okay.
taking advantage of that scalability
Right.
and flexibility that the cloud offers.
They were made for each other?
Yeah, kind of, in a way. So as data continues to grow
Mm-hmm.
in volume,
Volume, variety,
as we
volumes.
can expect even more innovation
Definitely.
in the database world.
Absolutely.
New technologies will emerge.
Okay.
Existing ones will evolve
Yeah.
to meet the challenges and opportunities
Of this data-driven era.
of this data-driven world.
It's an exciting time to be involved.
It is very exciting.
In the world of data.
And thanks to this deep dive,
Yeah.
you're well equipped
I feel a lot more equipped.
to understand and navigate this complex landscape.
Yeah, I really do. So
That's great to hear.
thanks for taking us on this journey
You're welcome.
of data exploration.
My pleasure.
We hope you've learned something
Mm-hmm.
and are feeling inspired to keep learning
Hearing.
about this fascinating field.
Stay curious.
So, until next time, happy data diving.
Happy data diving.